So we're going to continue on with this wing, straight tapered wing we were looking at last time. We're going to talk about formulas for the area, the mean aerodynamic chord, which is this average chord here. And then we also want to be able to calculate the distance, the x distance back to that chord, which would be this. I don't want a signature. And also the distance, the y distance out horizontally out to where the mean aerodynamic chord is. So that locates C bar in XY space. So we're going to have formulas for that. So we did the area last time. It's just an integration over the left side of the wing. We double it because we're only doing half the wing. And this is how the chord varies as a function of position along the wing, moving across. And then the mean aerodynamic chord we did last time. It's the area weighted average, so we divide by the total area. And we average C by multiplying by the area weight ds, integrate over the wing, and then we subtract out the area. Make sure biology would. 2, yeah, you're right. All right, and so then the formula for the x distance, so this is the x distance back to that mean aerodynamic chord. It's the same kind of formula, except that now we average the x distance back to that leading edge, right? The leading edge is tapering down. This is just the distance x down to that, and we're going to figure out the average distance down, and that's going to tell us where that C bar is. And then the distance y over, same formula, except instead of x, we're going to put y in there. And for that straight tapered wing, I gave you this formula last time. C as a function of y, so this is the C that goes into all of these formulas, is the root chord minus root minus tip times y over b over 2. And we had that last time. And remember, we said, well, at y equals 0, we're at the middle of the wing. So this is CR, and that's the root chord in the middle. And then if we go all the way out to the end at b over 2, this cancels out, the CRs cancel out, and we get CT, which was the chord at the tip. This is just geometry. There's nothing magical here. So if you use this into these formulas, and we also need a formula for x, so I'll give you that. Then you plug this into these formulas, and we can come up with, instead of having to do integrals, we can carry out the integration for the straight tapered wing that gives us formulas for all of these values just in terms of the parameters, root chord, tip chord, and so on. So x of the leading edge is y. So that's just trig. Y is the distance out. the angle is the angle down, and so that the tangent gives you the distance down, right? So we're talking the wings like here, the distance y is out here, this is the angle of the leading edge, and so that gives us the x distance down. So you use this formula. A more convenient one that he gives in the handout looks like this. Where he defines this sigma thing to combine the tangent into it. So it's just a different way. They've introduced b over 2, so if you plug this up here, it cancels the b over 2, and it just rearranges to get back to this. But sometimes that version is easier to use than the one up here. All right, so what you're doing in the homework is plugging this formula and that formula into all the integrals, carrying out the integration, and you're going to come up with this formula. And all of these formulas are in the Roscom handout as well.
Excuse me, Dr. Stick.
Now there's two forms for this. An easier form is this. All right, so I'm giving you the correct answers for that homework problem, and you're to carry out the integration. So make sure you show your steps, because that's what I'm going to be grading. The answers you already have. And do you remember what this lambda thing is? I think we defined that last time. It's the taper ratio. It's the tip chord divided by the root chord. It's just a collection of terms. Let's see, I gave you C bar and S and Y. The only other one you need for the answer is X mac. No, it's just multiplied. Yeah, good question. It's CR times that. And all this is pretty straightforward. The one that takes the most time is this one. It'll probably take you maybe half a page to a page. And to get to these answers I'm giving you, you're going to have to maybe rearrange and do some algebra to get it into this form. Remember what lambda is? So you'll have to get things rearranged so that you get this kind of stuff. So you might have to divide through by CR or something like that. All right, so we're going to do a really easy example wing. You're doing a harder wing. It's that straight tapered wing that's on the, yeah. Oh, is this off the screen? This one here? Yeah, okay. So I have to remember not to write past like right here. Good deal. Okay, so let me write it in. Thanks for the feedback. Yeah, I can't always watch the chat, unfortunately. Like that, so they can see that, right? Wait a minute, what am I writing? Oh, there's something under here, right? Did I write that before? Did I botch that up? It's 2/3 CR 1 plus lambda squared over 1 plus lambda. This is all multiplied. Okay, so you guys are doing the straight tapered wing that's pictured in your assignment. I'm going to do a rectangular wing. If I run out of time and I don't get to it, I need to give you the formula for the sweep of the half chord for the formula that you're going to need in the homework. So I think we're going to get to it. What time are we doing? Yeah, I think we'll be okay. But if I haven't written that formula up, tell me to jump to that formula to give it to you. Okay, here's an example. It's a rectangular wing. So the chord is constant, has a span of B, and we'll put in numbers in a minute. So I'm doing the easy one here. The root chord is equal to the tip chord is equal to C. What do you think the average chord of this one is? C, yeah, so we're going to get that. The taper ratio is 1. Told you I was doing an easy one. The sweep angle of the leading edge is the same as the sweep angle of the trailing edge, is the same as the sweep angle of the half chord, which is the formula I'm going to give you for the straight tapered wing for that thing in a minute. And so we can pretend that we don't have any formulas other than the integration. Go from scratch. This is easy because C is a constant, so it comes outside the integral. And the integral just becomes y evaluated between B and C over 2, or B over 2. So the 2 cancels out, the B goes in, and we get C times B. Sanity check, does that make sense? Is the area of that thing, yeah, it's a rectangle. Okay, how about C bar? Let's calculate that even though we know what it is. So it's C times dy, just straight formula, but C is a constant, so this is easy. We know the area now, it's C times B, and we get the integral of dy, which is y. So the 2's cancel out. I already put in the limits because it's just the same. And we get, I erased my boundary here, almost violated it. Surprisingly, we get C. So you can see that just from the integral formulas, you can take any shape wing, and as long as you know how C varies as a function of y, even though it's some wiggly weirdo shape, you can do this, and you can calculate the area. For the straight taper wing, you get those formulas that you just plug in the numbers, and you don't have to integrate once you've done it once, and you can calculate all this stuff. If you integrate over the formulas for Ymac and Xmac, Ymac is 2 over S Again, now this is ds, and we're averaging y. And so you integrate this, you get a 1/2 y squared. The 1/2 cancels with this. You carry out the integration, and you get b/4 if you do that. Because the c comes outside, so you're just integrating y squared. Does that make sense? Remember what that thing is calculating? It's calculating the average distance from the center line out to the average chord. And in this case, the chord's the same all the way along. So it's going to be 1/4 or 1/2 of the way along that half wingspan. What do you think x max is going to be? This is the average distance back from this leading edge to the top of the chord. What do you think that's going to be? Looks like 0, right? Well, it's because the sweep angle is 0. This is x to the leading edge times c dy, and x to the leading edge is always 0. So this thing turns out to be 0. Yeah, and they can see all the way down to the bottom, right? So we're good there. Okay, other stuff we'd want to calculate for this wing is what's its aspect ratio. And put an airfoil, build this thing out of an airfoil, what's its lift curve slope using that big formula. So that's next. So aspect ratio is b²/s. To go any further, we're going to put in some numbers. So let's say the wingspan is 5 meters and the chord is 1 meter. What's the aspect ratio? 25 divided by 5 times 1. Again, it's a rectangular wing, so the area is easy to calculate. So the aspect ratio is 5. We need this for that big formula. We're going to say, let's build this out of a NACA 0009 airfoil. So now we're getting a little more specific. Our wing is rectangular. Now we're saying there's the airfoil for it. So if you go to the airfoil data, just like you did on the quiz and you reviewed, and you're going to do in the homework, you get 0.1075 per degree, or 6.16 per radian. And as again, a sanity check, if it's per degree, it's going to be a number around like 0.1 for most airfoils. And per radian, it's going to be less than or near 2 pi. So if you get weird numbers, like if it's 455 per degree, then you know something's weird, or you've invented some amazing new airfoil. The other stuff we need, we're going to say Mach equals 0, which is what I'm asking you to do for the homework problem as well. Somebody sent me an email, so just do that for Mach of 0. We need the beta thing to go into the big formula, which is 1 minus Mach squared. So beta is 1. We need little k to go into the formula, which is CL alpha divided by 2 pi, all in radians. So we put the 6.16 in. And we get 0.98. And then we need the big K value. Try to draw my edge here. So where do I get big K? I need to show you. Go back to the handout from Roscoe. Here's the big formula and the plot that we're using. So we're getting all of the stuff that goes in here. A is the aspect ratio. There's little k. There's beta. We need the angle of the half-chord sweep. And big K comes from here. For an aspect ratio less than 4, use this formula here. For an aspect ratio greater than 4, use this formula. So our aspect ratio 5, so we use the bottom formula. It's easy because that's 0, because it's a straight rectangular wing. And this is 0. This is not going to necessarily be the case for you guys. I'm out of room here. Let's see. This is multiplied by 5. Close the bracket. Divide by 100. Again, I'm just filling in on that formula I showed you. And we get a value of 1.071. Yeah, and this thing here where I put in the zeros, this is the leading edge sweep angle here and here. You can see that from the formula. So I'm just plugging in numbers and I get this value, and now I need to go to the big formula. So I've got everything I need. I got the aspect ratio, did the airfoil, got CL alpha, got little k, got beta, got the Mach number, got the big K. I think that's everything I need for the formula. So let me share that again so everybody can see that real quick. Right, so I'm going to plug in. I got 2 pi in the numerator. I'm going to put the aspect ratio squared, beta squared, little k squared, 1 plus the tangent. The sweep angle of the half chord, it's a rectangular wing, so that's 0, makes it easy. Make sure I add the 4, make sure I get the 4 under the square root, and then I'm going to multiply by Ka for here. So that's what I'm doing. Big formula, so I need a big room here. So this is the lift curve slope. Notice capital L, so this is a finite wing. It's going to be 2 pi times the aspect ratio times big K, because I brought those over, multiplied through. So that's the numerator. The denominator, I got 2 plus the square root of a whole bunch of junk. So here's the aspect ratio squared, beta squared, little k squared times 1 plus the tangent of the sweep angle, which is 0. What's down there? That's beta squared And then make sure I add the 4 in. 4 goes under the square root. And if all goes well, should get this number. This formula is fraught with peril, just calculating it. So I highly recommend that you do it in steps. You don't try to punch this whole formula out in one fell swoop. You calculate like an intermediate answer for this, write it in, an intermediate answer for this. It's really easy to forget the plus 4 when you're before you square root. It's easy to forget to add the 2 before you divide. So I guarantee you, you'll punch it out the first time and you get a number. You'll do it again and you'll get a different number and you go, well, which one's right? And then you do it again and hopefully you get one of those 2 numbers or you get a third number. And then you call up your friend and you go, hey, what did you get for that big formula? And you can figure it out. And I don't mind you guys talking to each other on the homework and working together. What you turn in should be your own work though, not a direct copy of somebody else. I have no issues at all with you working in groups and working together to figure it out and compare answers. All right, so that's one of the homework problems for that straight tapered wing. Your sweep angle will be a little bit different here, and that's what I need to give you the formula for. And so this is pretty much the first step toward building an airplane, is deciding your wing shape, what kind of airfoil, and then how much lift you're going to get out of the wing you've chosen. And why do we care about that? Because we need to make sure we can get enough lift to balance the weight. Otherwise, we'll never get off the ground. So we're good on time, right? Yes. All right, so the formula for the tangent of the half-chord sweep line is and I need to draw a picture of the wing so we remember what these parameters are. All right, so this is the root chord here. This is the tip chord. What we're calculating is if we go halfway down, in other words, halfway of the root chord, and then halfway of the tip chord, we get what's called the half chord line. It's also halfway there and halfway there, right? So the angle that we're looking at is this. That's a horizontal line. This is how much that half chord line sweeps down. So the way this formula was calculated is we calculate this distance here, call it D, and then this is B over 2. And so the tangent of the half chord sweep angle is this distance D divided by B over 2. And you can calculate this distance D because you know that this is CT over 2, and this is the total thing here is CT, so you can take CT minus CT over 2, and that gives you that distance. And the same thing, you can figure out where this is because it's CR over 2 here, so that gives you the distances, and if you do all of that, you can figure out what that distance is. And in fact, that's where you start out with this formula. Oh, I forgot to tell you what xt is. Sorry. The xt is this little distance here. So that is the distance d that goes into the tangent. But then you do some algebra. So that use this formula to calculate it. And you can use the same picture to get the quarter chord sweep angle. I ran out of room, so let me start over. Because we'll need this later on when we're trying to calculate the mean aerodynamic center of the wing. Double checking my formula here. Yeah, so if you need the quarter chord, which means you're only going 1/4 of the way back, and you want the angle of that thing, that's the formula for that. That's xt times 2. So I guess we could write it. Like that to make it clear. Oh, and while I'm giving you formulas, this xt distance can be calculated if you know the trailing edge sweep, although you can also calculate it from other geometry. So if you ever need the trailing edge sweep angle and you know xt and b, you can calculate it from that. So again, the protocol for the homework is you have been working on it up to this point because you could do some of the problems. Finish it up, have it worked your first attempt on Monday. On Monday, we'll quickly go over it. I'll spot check answers so you can check your work. And then you upload it to Blackboard on Wednesday after you've had a chance to correct it. Okay, have a good weekend. Stay warm. And I'll see some of you here on Monday, the rest of you on Zoom.